Hello, good morning, students. How are you? Fine. Okay. Now let us start our remaining and last topic of this chapter: alcohol, phenols, and ethers. Hmm? So this is the last part of our chapter, that is ether. So ethers. About ethers, already we have seen definition and nomenclature of ethers. So what is definition? Just recall, ethers are alkoxy or aryloxy derivatives of alkanes or aromatic hydrocarbons. So these are ethers, and they can be represented by formula ROR or ROAR. That is, both of the valencies of oxygen are bonded with either alkyl or aryl group. Okay, its classification also we have seen: symmetrical ethers or unsymmetrical ethers. Symmetrical and unsymmetrical ethers. Okay, let us go ahead now. Preparation of ethers. Preparation of ethers. First, by dehydration of alcohols. Dehydration of alcohols. Dehydration means removal of water molecule from alcohol. When alcohol is heated with dehydrating agent like concentrated H2SO4 or H3PO4, two products, either ether or an alkene, can form depending on the temperature. So when dehydration of alcohol is carried out in presence of dehydrating agents like H2SO4 or H3PO4, okay, there may be two products, an ether or an alkene. So it depends on the temperature. For example, dehydration of ethanol by H2SO4, it gives ethoxyethane, that is ether formation take place at 413 Kelvin, while ethene, that is alkene, is formed at 443 Kelvin. Okay, so at this low temperature, 413 Kelvin, ether formation take place, and at high temperature, that is ethene formation take place. See, ethyl alcohol, two molecules in presence of H2SO4 at 413 Kelvin temperature, it gives ethoxyethane. See, these two molecules C2H5OH plus second molecule C2H5OH. So sulfuric acid acts as dehydrating agent. It is having strong affinity with water where there is present. Now here in these two molecules HOH, this water molecule get lost and it gives C2H5O C2H5. Ethoxyethane formation take place, C2H5O C2H5. Okay, when ethanol, reacts with sulfuric acid, but temperature is now 443 Kelvin. Here also dehydration, that is removal of water molecule, take place. Now let us see this ethyl alcohol. I have written in this way: CH2H bond CH2OH, that is CH3CH2OH, C2H5OH. Okay, so here this water molecule get lost. H, OH from the carbon and H from its adjacent carbon, this water molecule get lost, and here carbon carbon double bond formation take place. Okay, see here, symmetrical ethers can be obtained from primary alcohols by this method. Use of higher temperature or secondary or tertiary alcohol gives alkene as major product. If we use higher temperature or alcohol is secondary or tertiary, then the product is alkene. Okay, now first method by Williamson's synthesis. So by this method, simple as well as mixed ethers can be prepared. Okay, so this method is useful for preparation of simple as well as mixed ethers. Look here, general reaction: alkyl halide plus sodium alkoxide, oxide of this alkyl group, sodium alkoxide. So it gives, let me take pen, and ether formation take place plus sodium halide. Okay, if we take alkyl halide plus sodium aryl oxide, oxide of aryl group, aromatic ring. Okay, then it gives ROAR, alkyl group, and this is aryl group bonded with oxygen. So both simple as well as mixed ethers can be prepared by this method. This reaction follows this reaction follows SN2 mechanism. Here backside attack of nucleophile, which is alkoxide or aryl oxide, take place on alkyl halide. So on this alkyl halide, this ONA, alkoxide, sorry, OR, alkoxide, or OAR, aryl oxide, their backside attack take place, because here alkoxide or aryl oxide, they act as nucleophile. They act as nucleophile. So their backside attack take place. Why backside attack? In halogen derivatives of alkane, we have seen the front side is blocked by bulky leaving halide group. So nucleophile is attacked from backside to give transition state, and then the bond conforms and product formation take place. The alkyl halide used must be primary, because primary alkyl halides or SN2 reactions are favorable for primary alkyl halides. Okay, if we take tertiary butyl methyl ether, sorry, tertiary butyl methyl ether can be prepared by reaction of methyl bromide on sodium tertiary butoxide. If we have to prepare this tertiary butyl methyl ether, it can be prepared by using methyl bromide, because this methyl bromide is primary primary alkyl halide. Okay, so sodium tertiary butoxide, this tertiary butoxide nucleophile will attack from backside on this carbon, primary carbon, and it forms tertiary butyl methyl ether. If instead, if we take here tertiary butyl bromide and sodium methoxide, so instead of getting ether, we will get corresponding alkene. We get alkene because the halide is tertiary, and this tertiary alkyl halide is favorable for SN1 reaction mechanism. So CH3CONA plus methyl bromide. This nucleophile attacks on this carbon and it forms tertiary butyl methyl ether. It forms tertiary butyl methyl ether plus sodium bromide is the byproduct. See again here, if secondary or tertiary alkyl halides are used, the reaction leads mainly to alkene formation. See here, if tertiary or secondary alkyl halides are used, the reaction goes in the favor of formation of alkene. That is elimination reaction. For example, see here, this halide is tertiary alkyl halide, tertiary butyl chloride plus sodium ethoxide, sodium ethoxide. Now, instead of the backside attack, because this tertiary carbonium ion, this tertiary carbonium ion is stable and it is favorable for SN1 reaction only. So here hydrogen from this carbon and chlorine from this adjacent carbon get eliminated, and here carbon carbon double bond formation take place, giving corresponding isobutene, corresponding alkene plus ethyl alcohol. Okay, aryl halides do not give Williamson's synthesis. Now physical properties, physical states and boiling points. First, dimethyl ether and ethyl methyl ether are gases. Other ethers are colorless liquids with pleasant odor. Second, lower ethers are highly volatile and highly inflammable substances. They are volatile and highly inflammable substances. Third point, boiling points of ethers show gradual increase with increase in molecular mass. See here example of ethers, and here their boiling points are given. Dimethyl ether 248 Kelvin, ethyl methyl ether 284, one alkyl group is increased, so molecular mass increases and the boiling point also increases. Here diethyl ether, again one methyl group on this side, one methyl group on this side, increase in this diethyl ether than this dimethyl ether. So boiling point increases 308 Kelvin. Okay, so by increasing molecular mass, the boiling points of ethers goes on increasing. Now polarity and solubility. Since carbon, oxygen, carbon, this bond angle is 110 and not 180 degree. The dipole moment of two carbonyl bonds does not cancel each other. Therefore, ethers possess small net dipole moment. For example, dipole moment of diethyl ether is 1.18 d by 1.18 d by unit. D by is the unit of dipole moment. Now see here, as this bond angle is 110 degree, if this bond angle is 180 degree, that is R is here and second R is here, R, O and this R, if they are in straight line, then the bond angle will be 180. If bond angle is 180, then the polarity made by this RO bond and this RO bond, they will cancel each other and total dipole moment will be 0. But this bond angle or RO and R, these are not in straight line. They have this 110 degree bond angle. So this polar bond carbon oxygen, this polar bond and this carbon oxygen polar bond, it is having certain net dipole moment. It is in this direction. Let me show. So this polarity, this dipole moment of RO bond, and for this RO bond the dipole moment, and this is net dipole moment in this direction. So net dipole moment is 1.18 d by unit or d by unit. The intermolecular hydrogen bonding in alcohols is not present in ethers and alkanes. We have seen in alcohols there is intermolecular hydrogen bonding which is not present in ethers and alkanes. But the solubility or miscibility of ethers in water is similar to that of alcohols of comparable molecular mass. There is no intermolecular hydrogen bonding in ethers. Intermolecular hydrogen bonding is present in alcohol. Okay, and because of this intermolecular hydrogen bonding in alcohols, alcohols having higher boiling point, higher boiling point. But in case of ethers and alkanes, there is no intermolecular hydrogen bonding. But what happens in these ethers about their solubility? Ethers are soluble or miscible in water. Why? Because the oxygen, because ethers can form hydrogen bonding with water through ethereal oxygen, through ethereal oxygen. So this is ethereal oxygen, and this Ethereal oxygen having partial negative charge. This can form hydrogen bonding with H plus ion of water molecule. So here this is intermolecular hydrogen bonding. This dotted line is, and it show miscibility. Because of this hydrogen bonding, or ethereal oxygen can form hydrogen bonding with water molecule. Hence, ethers are miscible or soluble in alcohols. Sorry, soluble in water similar to that of alcohols. Okay, but alkanes do not have hydrogen bonding, so they are not soluble in water. So this is the reason behind their solubility. Comparative boiling points of alkanes, ethers, and alcohols. N-heptane, methyl N-pentyl ether. Their molecular mass is nearly same, 100, 102, and N-hexyl alcohol, 102. Okay, nearly similar molar mass, but different compounds are taken. This is alkane, this is ether, and this is alcohol. Their boiling points are as this: 371 Kelvin. For ether, it is 373 Kelvin. Because no hydrogen bonding, so their association with different ethereal molecules is very weak or similar to that of N-heptane. So just slight difference in this, in their boiling points. But see here, N-hexyl alcohol 430 Kelvin, higher boiling point, because one N-hexyl alcohol is bonded to another N-hexyl alcohol molecule through strong hydrogen bonding, and hence to break this strong hydrogen bonding, intermolecular strong hydrogen bonding in alcohols, quite more amount of energy, heat energy is required, and hence the boiling point is higher. Okay, chemical properties of ethers. Ethers are neutral in aqueous medium. They are neutral in nature. Ethers do not react with base, cold dilute acids. Third, ether do not react with, third point, ethers do not react with reducing or oxidizing agents and active metals. Because they are neutral, they do not react with bases, cold dilute acids, not react with oxidizing reducing agents, no reaction with active metals. Fourth, ethers dissolve in cold concentrated H2SO4 due to formation of oxonium ion, oxonium salt. See here, this is ether. How this oxonium ion, oxonium salt formation take place? See ROR, and here H plus, H plus, and OSO3H minus. This is H plus, and OSO3H, SO3H, that is H2SO4 minus. So here the unused electron pair on this oxygen electrophilic attack of H plus ion take place here, and it forms oxonium salt, oxonium salt of ether. This is salt because this is plus ion and this is minus ion, OSO3H minus ion. Okay. Reactions involving alkyl group of ether. Reactions involving alkyl group of ether. Ethers combined with atmospheric oxygen to form peroxide, CH3CH2O C2H5, diethyl ether plus oxygen, atmospheric oxygen, long contact with air. If this ether comes in contact with air for long time, then peroxide of diethyl ether formation take place. That is CH2. Here it was CH2, and in one of the CH bond, this both oxygen get added. So COOH. So this is peroxide linkage. This is peroxide linkage, and hence it forms peroxide of diethyl ether. Now reactions involving CO bond. Reactions involving CO bond. CO bond cleavage. First, reaction with hot dilute H2SO4, that is hydrolysis. Ethers when heated with dilute sulfuric acid, it undergoes hydrolysis to give alcohols or phenols. See, this is first example, ROR, symmetrical ether. ROR, symmetrical ether, when it reacts with HOH in presence of H plus ion, that is in presence of dilute acid. What happens? See, HOH. See this written with pen. H bond OH, it breaks here, that is carbon and this oxygen bond, this breaks, carbon of this alkyl group and this oxygen, this bond breaks in this way. So one molecule of ROH and second molecule of ROH formation take place. See here, this is symmetrical ether. This both alkyl groups are same. So we are getting two molecules of similar alcohol. In this second example, ether is ROR dash. That is mixed ether. It is mixed ether because this R and this is R dash. They are not similar. So when undergo hydrolysis, acid hydrolysis in presence of H plus heated, it gives ROH and R dash OH. Mixture of two different alcohols are obtained because this is alkyl group R and this is alkyl group R dash. So mixture of different alcohols is obtained. If alkyl aromatic ether AROR, this mixed ether is taken and followed with hydrolysis in presence of H plus ion, it gives one phenol, AROH, and second molecule of alcohol. Got it? So this is because of cleavage of CO bond. This reaction is because of breaking of CO bond. Now ethers react with PCl5, second reaction. It gives alkyl chlorides. It gives alkyl chlorides. Now here ROR dash plus PCl3. ROR dash ether, mix ether plus PCl3 on heating, it gives mixture of both different alkyl halides, alkyl chlorides, RCl plus R dash Cl plus POCl3, phosphor, phosphoryl chloride. Third reaction, look at this reaction. Reaction with hot concentrated acid. Alkyl ether reacts with hot and concentrated HI and HBr to give alcohol and alkyl halide. When ether reacts with hot and concentrated HX, it gives the mixture of alcohol and alkyl halide. The order of reactivity of HX is HI is more reactive than HBr, which is more reactive than HCl, because it depends on the size of halogens. Iodine is bigger in size than bromine than chlorine. So smaller chlorine forms bond with hydrogen, it is shorter bond. Shorter the bond, stronger is the bond. So less reactive. Here, because of increased size of bromine than chlorine, the bond is slightly weaker than HCl. So it is more reactive. But in this case, iodine having bigger size, and hence the bond is longer bond, and hence it is weaker bond. So it breaks easily and reactivity of HI is greater. See this reaction, ROR simple ether plus HX, it gives ROH, alcohol of this alkyl group and alkyl halide of this alkyl group. So alkyl halide plus ROH formation take place. One is alkyl halide and second molecule is alcohol. When mixed ether, that is aryl alkyl ether, is taken, they have stronger and shorter bond between oxygen and aromatic ring. See this oxygen and aromatic ring, this bond is shorter than this oxygen and this carbon, because this is sp3 hybridized carbon and this is sp2 hybridized carbon of aromatic ring. So here this bond is shorter bond, hence stronger bond. So when HI reacts with this, instead of breaking this shorter bond, this slightly longer or larger bond undergo cleavage, and phenol is the product and halide of alkyl group. Okay, alkyl halide and phenol formation take place. So such ethers undergo reaction with this concentrate hot and concentrated HI, always form phenols, and alkyl halide. Now, next property, electrophilic substitution in aromatic ethers. The alkoxy group in aromatic ethers is a ring activating and ortho para directing group towards the electrophilic aromatic substitution. This is evident from the resonance structure. If we draw the resonating structures of this aromatic ethers, so RO, and this is benzene ring, alkyl group, and this is aromatic group. So here this plus inductive effect, plus resonance effect of OR group, it increases electron density at ortho para, this is para and this is ortho positions. Because of presence of OR group, the electron density in benzene ring at ortho position, that is this position ortho, this position para, again this position is ortho. On these positions, electron density increases, and this increased electron density at this ortho and para positions, so it is said that this aromatic ring in ethers is activating and ortho para directing. That is, electrophile will attack at these stable positions, that is ortho, para and ortho positions. See how this electron density increases. Resonating structures, we have seen these resonating structures in halogen derivatives of alkanes also. So here electron stabilize, that is negative charge stabilize at this position. Its resonating second structure, negative charge stabilize at this third position. Third, in this third structure at para position, again stabilizes at this ortho position in the fourth structure. So negative charges are stable in this second, third and fourth structure at ortho and para positions. So at this negative charges or at this ortho and para positions, the electrophile may attack to give the product. Okay, see, look carefully all these five structures, resonating structures, how this negative charge is stabilized at ortho, para and ortho positions. Okay, so all these are resonating structures. See, first halogenation, anisole, that is benzene ring OCH3, this is ether CH3O, and phenyl ring, it is called as, or its common name is anisole. When anisole undergo bromination with Br2 in presence of acetic acid, in presence of acetic acid, it gives a mixture of ortho and para bromo anisole. It is due to activation of benzene ring by methoxy group. So this is methoxy group. So it is activating at ortho and para positions. So this is para position and this is ortho position. So Br plus get attacked at this para position and at ortho position. So this is major product. Parabromoanisole is major product than orthobromoanisole. Here this OCH3 group and Br, OCH3 minus and Br minus, both are living groups or both are bulky nucleophilic nucleophiles now. So they are far away from each other. So this structure is stable. But here, because of in these two bulky groups, they are very close with each other. Because of steric hindrance, they repel to each other and this structure loses its stability. So this is less stable, 10%. Friedel-Crafts reaction, second reaction. Anisole reacts with alkyl halides in acyl chloride in presence of anhydrous AlCl3. In presence of anhydrous AlCl3, alkyl halides and acyl chloride. So this is alkyl halide in presence of anhydrous AlCl3. So CH3 plus and Cl minus. So here at this position and at this position the negative charges are more stable. So this and this both positions are ortho. So electrophilic attack take place either at this position or either at this position. Okay. So here 4-methoxytoluene, this is major product, and 2-methoxytoluene, this is minor product. Okay. So this is Friedel-Crafts alkylation. This is Friedel-Crafts alkylation. Why alkylation? Because alkyl group is introduced in benzene ring. Alkyl group is introduced in benzene ring. Okay. And here Friedel-Crafts acylation. CH3 COCl. So and this is minus. So this acyl group may attack at this ortho position or it may attacks at this para position. Okay, in presence of anhydrous AlCl3. So COCH3 and this is COCH3. It is 4-methoxy acetophenone and this is 2-methoxy acetophenone. Nitration. Anisole reacts with concentrated HNO3 in presence of nitrating mixture sulfuric acid, concentrated sulfuric acid, to give mixture of orthonitroanisole and paranitroanisole. So here HNO3 HO can be written as HONO2 NO2. This is plus and this is OH minus. Okay, so this electrophile either attacks at this position or it may attacks at this ortho position with liberation of two water molecules. From this position, one hydrogen is removed, goes along with OH to form one water molecule, and from this one hydrogen eliminates and goes with this what OH, it forms 2H2O as byproduct. So 4 nitroanisole 4 nitroanisole and 2 nitroanisole, major and minor products. Now uses of alcohols, phenols and ethers. Uses of alcohols. Methyl alcohol is used as solvent for paints and varnishes. Ethyl alcohol is used as antifreeze agent in automobile radiators. It is also used as solvent. Okay, phenols. It is used in preparation of phenol formaldehyde resins. For example, bakelite. In polymer chapter we will see this. We have seen already this formation of bakelite by using phenol formaldehyde resin. Second, phenols are used as antiseptic in common products like air fresheners, deodorants, mouthwash, floor cleaners, etc. And uses of ethers. Earlier, diethyl ether was used as general anesthetic in surgical operations. For surgical operations, diethyl ether it was used for anesthetic as anesthesia. Okay. Second, diethyl ether is used as solvent for Grignard reagents, fats, waxes, and oils. Okay, so these are uses of alcohols, phenols, and ethers. So in this way, we have finished this topic: alcohols, phenols, and ethers. So prepare this topic by reading carefully line to line from your textbook and solve the questions given back of the text. Okay, let us stop here. Thank you.